Welcome everyone to a brand new explainer. Today, we're unpacking a really absolutely brilliant piece of research. It's tackling something massively ambitious, teaching machines to finally understand human movement exactly the way we do. The paper is titled An Elastic Shape Variational Autoencoder for Skeleton Pose Trajectories. Yeah, it's a mouthful, I know, but trust me, the core idea here, it's a total game changer for how we interact with technology. Let's get right into it. Okay, let's dive into this. Picture yourself sitting at a park, just people watching. Your brain does something incredibly fast, almost effortlessly. You don't just see, a random collection of limbs moving around. You instantly recognize, oh, they're walking, or that person is running, or maybe even, hey, they've got a slight limp. But if you feed that exact same video to a standard AI and ask it to track the human skeleton, it gets completely overwhelmed. It is literally blind to what's so instantly obvious to you and me. So to understand how researchers actually solved this blind spot, we're going to walk through 6 structured sections today. We'll start with the AI motion blind spot. Then look at how they mathematically stripped away visual noise, explore AI in curved space, see how this geometry diagnoses strokes, tackle the micro-movement challenge, and wrap up with the future of spatial computing. All right, section 1, the AI motion blind spot. Standard AI models waste a massive, and I mean massive, amount of computational energy when they analyze video. Why? Because they get totally lost in the physical camera setup instead of focusing on the actual person's geometry. To an AI, human movement isn't an intuitive physical action. It's just a chaotic blizzard of changing geometry. Our brains, we instantly grasp the shape and motion no matter the context. But a standard neural network, it gets entirely bogged down by everything else going on in the frame. The big hurdle here comes down to what researchers call nuisance variables. Think about it like this. Imagine filming your golf swing from the front and then again from the side. You know it's the exact same swing, right? But to a standard neural network, a tall person swinging fast while facing left looks like a completely different action than a short person swinging slowly while facing right. It completely misses that they're doing the exact same core action, just at different speeds or angles. The AI has to burn through a huge percentage of its processing power just trying to calculate and compensate for these totally superficial variables. Which brings us to section 2, stripping away visual noise. So the big question is, how do we force the AI to ignore the camera angle, ignore the person's height, and just look at the pure, raw movement? Well, the researchers use an elegant mathematical framework based on something called Kendall shape space. And this is where it gets cool. Think of it like a star-shaped cookie cutter. The shape of that star is mathematically identical whether you cut it from a giant sheet of dough or a tiny little scrap, and it's identical whether you hold the cutter sideways, upside down, whatever. The intrinsic starness doesn't change. Kendall's shape space essentially forces the AI to only look at that pure intrinsic cookie cutter shape. To actually do this, algorithms use 3 specific steps to quotient out or filter out these physical space variables. Step 1, they remove translation. That's basically just where you're located in the room. Step 2, they remove scale, so how tall you are. And step 3, they remove rotation, which is the exact direction your body is facing. By doing this, the algorithm literally collapses infinite viewing angles into one single, unified mathematical identity. But human motion isn't a static cookie, right? It happens over time, and we all move at wildly different speeds. To fix this temporal issue, they use something called a transported square root velocity field, or TSRVF. It sounds complex, but just imagine 2 audio tapes of the exact same song. One is played at double speed, the other at half speed. If you compare them second by second, it just sounds like chaotic noise. What the TSRVF does is mathematically stretch and compress these motion trajectories until the beats perfectly align. It completely synchronizes the core actions, regardless of how fast or slow they were originally executed. Now, what's really interesting about this slide is how it all comes together in the ES-VAE architecture, the Elastic Shape Variational Autoencoder. Once the movement is mathematically purified into tangent vectors, it goes into the encoder. The encoder takes this complex 3D movement and squashes it down into a tiny bottleneck, which is the latent space you see represented by that Gaussian distribution right in the middle. It's kind of like summarizing a 1,000-page novel into just 3 words. Then the decoder steps in and tries to rebuild the entire movement using only those 3 words. By forcing the neural network to perfectly reconstruct the skeleton trajectories from such an incredibly restricted mathematical bottleneck, it guarantees the model is capturing the absolute, unadulterated essence of the physical motion. Let's move to Section 3, AI in Curved Space. You see, abstract math is super easy to manipulate on a flat whiteboard. But human movement exists in a complex 3D world, constrained by the joints and limits of our physical bodies. So the researchers had to prove this AI actually understands curved, multidimensional space better than standard AI. And this visualization brilliantly illustrates that exact test. They generated noisy data along a winding, nonlinear curve on a 3D sphere. A standard Euclidean AI essentially thinks the world is flat. If you look at the tangent PCA and standard VAE lines there, they're trying to draw straight lines or they just deviate wildly. They totally fail to trace the true curve. But look at that solid black line. That's the ES-VAE. It beautifully and accurately hugs the exact twisting underlying curve right through all that intense background noise. It proves it actually understands the true geometry of the space. All right, Section 4, Diagnosing Stroke Through Geometry. Because the model is so exceptionally good at finding the true shape of noisy data in curved space, the researchers brought it into the real world. They analyzed a clinical dataset of 155 participants, a mix of healthy individuals and stroke survivors, to see if the AI could diagnose human movement anomalies. The goal was to predict a patient's PULMA score, which is a clinical measure of balance and gait severity. Look at these results. The ES-VAE hit an R-squared value of 0.74. Now, in statistics, that means the model can explain 74% of the variance in a patient's mobility score. For human biomechanics, which is naturally super chaotic and noisy, hitting 0.74 is a massive signal. It completely crushed standard deep learning models like LSTMs, which only hit 0.64, and basic PCA models at 0.44. It shows this geometry-aware approach is just vastly more accurate for clinical predictions. Now, you might be wondering, how do we know the AI isn't just making a lucky guess based on digital background noise? Well, look at this visualization of the latent variables. The AI compressed the complex movement down to essential modes of variation. And this first one here, variable Z1, it perfectly isolates a shorter stride length combined with stiffened limbs. Guys, that is the literal textbook medical definition of a hemiplegic stroke gait. The AI independently discovered the medical definition of a limp purely mathematically, entirely on its own. It was never explicitly programmed to look for it. And it gets better. Check out the correlation matrix here to see how this builds into an incredible diagnostic tool. Focus on variable Z4 on the x-axis. Z4 isolates unilateral arm variability, meaning it mathematically recognizes when one arm swings normally while the other stays rigid. The AI actually correlated the specific geometric anomaly directly to lesion laterality. Basically, it could link the physical movement back to the exact left or right side of the brain where the patient's stroke lesion occurred. That is an astonishing bridge between what is usually a completely black box AI and a highly interpretable, actionable medical tool. Moving on to Section 5. The Micro-Movement Challenge. Identifying a severe medical limp is one thing, right? That's a macro-level deviation. But what about subtlety? The researchers wanted to push the absolute limits of this model with a micro-movement challenge. Can an AI tell the difference between everyday actions that look almost entirely identical? They use this brutal dataset called NTU60, which focuses on highly confusable hand-to-face motions. Think drinking water, eating, brushing your teeth, making a phone call. The static body poses for these are virtually identical. Trying to differentiate them is like trying to read delicate handwriting while bouncing around on a moving train. Standard AI just gets completely overwhelmed by the bumping of the train. But by using Kendall-shaped space to essentially stop the train and flatten out the paper, the neural network could devote 100% of its focus to analyzing the shape of those micro-movements. And the result? The ES-VAE achieved 0.56 macro F1 score on this adversarial dataset. That more than doubled the standard vanilla VAE score, which was stuck at 0.27. It proved conclusively that when you mathematically strip away the noise, you free up the computational capacity needed to spot those tiny, incredibly subtle trajectory differences. Which brings us to our final section, Section 6, the future of spatial computing. This framework represents a total paradigm shift. We're moving away from simply throwing more data at an AI to giving the AI better geometry. Because this mathematics, it's really the foundation of the next generation of spatial computing. In their future work section, the authors proposed layering in EMG signals, the actual electrical firing of your muscles.
Just imagine a geometry-aware AI that maps the perfect physical shape of how your skeleton moves, while simultaneously tracking the invisible electrical symphony of the nervous system driving it right beneath your skin. The possibilities for things like advanced prosthetics or continuous, highly personalized rehabilitation tracking are truly boundless.
We are moving from devices that simply record flat pixels to systems that genuinely comprehend our physical dynamics. We are finally teaching machines to read the language of human movement, and they are actually starting to understand the vocabulary. So how will machines learning the true geometry of our bodies change human-computer interaction forever? It's a huge question. Thank you so much for joining us for this explainer. Keep exploring the shape of the world around you, and remember, sometimes to truly understand the movement, you have to find a way to strip away the noise.